Questions?
First homework or
Sorry?
This is
Is there any mistakes?
no.
No, I just tried that one problem is about quantum mechanics.
It's done by purpose. Because I don't know whether Professor Yevtushenko discussed with you two-dimensional well and existence of shallow level and two-dimensional well. I would like to see what you know about this and whether you know the depth of the level and whether you know that this energy level always exists for arbitrary shallow well. It's just
It's related to the couple bias at the surface Fermi's.
it's related, yes. It's actually related to Cooper pairing problem and BCS theory in some literal sense, because of course Cooper pairing is not bound state, as we probably discussed many times in the course of superconductivity, and this problem is about bound state. So I just would like to see how you solve quantum mechanical problems. It's a very simple one. Good, but two other sections, namely Bose-Einstein Fermi gas and magnetism, cover some topics of what we discussed. You see, problems are very simple, and you have almost 3 weeks to complete this homework. As I said, please write a solution in clear and written script. Put your name on the top. Please stick it together and put it in my mailbox. So I will collect it on April 26th in the morning, and we discuss some of this problem on April 27th during the last meeting before exam. I sent this as a file to Federica. Did somebody used to contact Federico or can take extra copy for him?
Maybe I know it's good.
Yeah. In any case, I sent it to him as a PDF file. Good. So everybody is present, right? Or there is one person missing? You. Good. Okay, so we have 3 last lectures and 2 extra lectures which I promised to give you after exam. So this is number 1. The tutorials, everything is short and clear. I talk to my assistant. Did you get the schedule of tutorials, by the way? Then what else? Homework is given. Is there anything else important? So it might happen that Thursday lecture, or I think Thursday lecture will be transferred to Friday. I'm not yet sure that it will happen. But let's see, because on Thursday we have some important meeting in the group, and I'm afraid I might be busy or just escape from this meeting, which actually is not a very good idea. So let's see. Please don't be surprised if Thursday lecture is moved, is shifted, but if not, then okay. Fine. Any questions regarding the previous lecture? As I said, I only copied files on the memory stick and will give it to Patrizia as soon as she will be here. I copied even more, so what you will get as a printout, this PowerPoint presentation for water gases, for cold gases, which was before we started the chapter about magnetism. Then you will get the presentation on strongly correlated systems, which we discussed during last lecture. You will get some summary about magnetism, which I don't know. If time permits, we do it on last lecture. Just repeating summary of magnetism with the PowerPoint, because I planned for last lecture to summarize the discussions of whole course. And this is what the PDF files which I give to Patrizia. And after two last lectures, you will also get a printout of these two lectures as well. As I said, I will try to collect all recordings of these lectures on a DVD. And after little programming with HTML script, I will give you a syllabus of lectures with linked links to files of recordings, so you will get whole course on one DVD, and there I will also enclose PDF files of all presentations you got during this course. Yes. Okay. Then today's lecture will be devoted to interacting electrons, so electrons with Coulomb interaction. And tomorrow we discuss electron systems with disorder, namely weak and strong localizations and mesoscopic phenomena in disordered systems. Okay, so this is rather chapter, and what we begin with is definition of the electric function. So let me put sub-paragraph. So the plan for today's lecture is to discuss the properties of the dielectric function as a response on Coulomb interaction in the system, derive using Maxwell equations and simple time-dependent perturbation theory, so-called polarizability of medium, and discuss properties related to this polarizability, namely screening in the electron system subject to Coulomb interaction, then plasma modes existing in the system, and so-called Confederate oscillations in the system. Okay, let's start with the definitions, and let's question, not? Let's start with simple Maxwell equations for inductivity. So D is a field in the medium. So in the notations which you probably used to have, so this is 4 pi rho external times E. So this is a charge, total charge, this is one over second pair of Maxwell equation, and another equation I will write for electric induction. So this is rho total times E. So I deliberately put E as a charge and the rho as a density in order to have this difference. So this is a response to external charge, and this is total charge in the system. Okay, I don't need any Maxwell equation which contains the special and time derivatives of the magnetic induction, so I'm just considering electrostatics. Okay? Good. If I take a Fourier of these equations, namely coming from RT to Q omega, I will have I Q times D Q omega is equal to 4 pi E rho external Q omega, as well as I Q in Q omega is equal to 4 pi E rho total Q omega. So by the definition, the electric constant is a proportionality between D and E. So let me be more precise. I will write the parallel component is Q omega is equal to epsilon Q omega times E parallel Q. So this is the electric function. So if we use two Maxwell equations, we find out that epsilon Q omega is nothing but rho external Q omega divided by rho total Q omega. And if we write that rho total is just rho external plus rho induced. So the charge which is induced in the system when you put some external charges into it, we can write down that E epsilon Q omega is equal to 1 minus rho induced Q omega divided by rho total. This is a function we will be given to. Of course, if we are talking about interaction, so if we are interaction in the system is E squared over R, the interaction, which after taking Fourier transform in 3D, it's 4 pi E squared over Q squared. Effective interaction, V effective, will be 4 pi E squared Q squared epsilon Q omega. So we study today how does this function look like and what is the effects of dynamical and static effect in the electric function and how they manifest itself in the form of effective interaction. So did you discuss it in the course of solid-state physics? Did you discuss properties of the electric function in metals? For example, the trivial fact that metals are so shiny is encoded in this function. And we see after simple calculations basically why the metal are so different from insulators from the optical point of view.
But we discussed about the absorption coefficient.
Sorry?
Absorption coefficient.
Absorption. Okay. But did you discuss it through the electric function? Okay. In order to proceed with the calculations, and I will not do anything more complex than using time-dependent perturbation theory, I will need to refresh you and some basic things about quantum mechanics and basic things about time-dependent perturbation theory. So, if you are okay with the statement of a problem, what we are discussing today, I will write down a few lines about quantum mechanics. So first of all, let's write second quantized form for the density operator. You see that the density of charge, is just equal density times E. So I will be dealing with density rho R, which is the sum over atoms delta function R minus. By the definition, we have charges in the position A, regardless whether these are lattice position or we have plasma. I'm not specifying whether the summation is taken in a crystal with rotation invariancy or not. And what I would like to do is to write down the secondary quantized form of this operator. We know that this is single particle operator, by the way. Density. In secondary quantized form of single particle operator are, we write it down as a sum over k prime, k prime, a divided k sigma, a k times sigma. Where from the advanced quantum mechanics course, second quantization, we know that matrix element a k prime is just integral over dRA. And I have to take the wave function at A, this operator delta R minus RA times psi RA. So, and if I take this integral, and let me put index k, I will see that these functions are closed waves. So k is a quantum number which is nothing but momentum. So we have here psi k star r psi k prime r. But we know that in the basis of occupation number, namely if we take rho n and A are fermionic operator, only diagonal term survives. So namely, it is proportional to say k Okay. Delta k, k prime, and k. So when I will take a summation, I will write it down as the sum of k sine k r modulus square times. So psi is a wave function which in the first approximation will be considered as a plane wave, and here I put index sigma, which is a spin projection up and down. So what I need, the first ingredient I need is this form for density operator. Rho, let me write now down R and T is sum over k, sine k r t modulus square times m k sigma in sum over t. So what I will use is perturbative calculation of the wave function. Perturbative means, to begin with, I start with non-interacting electrons, namely plane wave function, and then I take into account effect of interactions as a custodial perturbation, recalculate wave functions including effect of interaction, and then calculate induced charge in the system, and after calculating induced charge, I will arrive at dielectric constant, which I will call you in omega is equal to 1 minus rho induced. Omega divided by rho. Okay. However, in order to do it, I will use some special approximation in order to proceed with this calculation. This special approximation is called random phase approximation. Which actually is kind of mean field. And what does it mean? It means that I will introduce some external potential, V external, as V e to the power I Q R minus omega T plus complex conjugated, and I will totally ignore any fluctuations in the system, considering that all responses for that kind of Fourier harmonic will also be proportional to the same Fourier harmonic. So I will exclude any phase coherence effect, assuming phases in the wave function random, so to say. I will disregard all possible interference effects, which we will discuss tomorrow. So this is why it is called random phase approximation. And in the spirit, this is pretty the same style which we used in order to calculate the susceptibility of Heisenberg ferromagnets above Curie point. You remember, I mentioned it as mean field approximation. We also calculated some response function as a response to Q dependent magnetic field, static one, because I didn't want to proceed with dynamical effects. So the same spirit will be used there. But I remind you for Coulomb interaction, when the Coulomb gas can be considered as weakly interacting. We already discussed it once. In order to see effects of interaction to be small, we have to have a condition that potential energy is much smaller compared to kinetic energy. And if kinetic energy is h squared over m a squared, and potential energy is e squared over a, where a is a typical distance between electrons. So we may write down that A is of the order of inverse Fermi momentum. We have to have this condition. If we write it down, we can write it as A is much smaller than h squared over m squared. And this is, we know what it is. This is Bohr radius, or finally, condition reads that Pf times Bohr radius is much larger than 1. So the Coulomb gas of electrons becomes more and more ideal at high density. So this is why metals are described by sometimes approximation of weak Coulomb interaction, but as long as insulators are concerned, they are never case for weak interaction at all. To say nothing that insulators cannot have Fermi momentum. Then tomorrow we discuss criterion of localization, so to say simple criterion. Yeah, but the point is, you remember from our first lectures that the density of electrons in non-interacting electron gas is proportional to Fermi momentum to the power cube in three-dimensional square. In two-dimensional case, therefore, this condition, namely Fermi momentum times Bohr radius is much larger than 1, means that the density times Bohr radius cube is much larger than 1. We should have high density electron gas, and in that case, we can consider it as weakly interacting. So potential energy in that case is indeed smaller compared to kinetic energy of the electron, which is Fermi energy. Okay. Good. After reminding you that, let me give you a second portion of quantum mechanical information which we need, namely what it is time-dependent perturbation theory. Let's start with non-interacting electrons. So the wave function characterized by the quantum number k, and I will put node here as a function of r t. That's plain words. E to the power I k r minus epsilon I epsilon k t, and I will put normalization of the volume. So omega here is the volume of the system in order to avoid any confusion with V, which for this lecture denotes the interaction. Okay?
Excuse me, so we are calculating for metal system. It's not for dielectric.
No, of course we will be calculating for metal. And today we will be only discussing metals. Sorry. Of course, I can comment at the end of the story what are the properties of insulators, but at this very moment, let's specify it from the very beginning. We do consider metals with weak Coulomb interaction in that. So, as a result of incorporating effect of weak interaction, namely calculating the induced charge in the system, and then defining the electric constant, we will be calculating Q and omega dependent dielectric constant for metals. Okay. So, you remember how perturbation theory, time-dependent perturbation theory looks like. We will be looking for CKRT as a sum over K prime C k prime t psi node k prime r t. At 0 level, all k prime not equal to k, ck prime is equal to 0. For k prime equal to k, ck is equal to 1. So this is zero order perturbation theory. What we have to do is to plug in this function into our Schrödinger equation. D psi over dt is equal to h psi. Then we use the fact that h is equal to h node plus d, and psi node are eigenfunctions d psi node k over dt is equal to h node psi node k. So these functions are eigenfunctions of non-interacting Hamiltonian, and h node for this particular case is minus h squared 9 over 3. Well, sum of all particles. Okay, so if we do that and differentiate this wave function with respect to time, we have two terms. First term corresponds to differentiation of this term. This will have a counterpart in the Hamiltonian, since the wave function is expressed as a summation of a complete basis of the wave function. But secondly, there will be derivative sum over k prime d over dt ck prime t times psi k prime r t, and this is equal to sum over k prime v c k prime sum no k prime. Okay, so what I did, I dropped the term in the left-hand side containing the derivative of psi node, and I dropped term in the right-hand side containing h node. So what I should do now, I have to multiply the right-hand side and the left-hand side of the equation on psi k node and star and integrate over dr. Right, for simplicity, to distinguish that here summation is different. Of course, I use the fact that integral dr psi star node k psi k prime node is proportional to delta k k prime. So I have orthogonality of my wave functions. As a result, I'm recalling to what you have to know from advanced quantum mechanics course how the perturbation theory with time dependence looks like. I have d over dt c k is equal to, here I will have a matrix element, so integral over dr psi k node star v r psi k double prime is equal to v k k double prime. So this is a matrix element of interaction. Therefore, I have sum over k double prime V K K double prime C K double prime T. Okay? So the last thing, I will use the fact that into the right hand side I have to plug in the results of zero order perturbation theory. Namely, that C K equal to 1 for K equal to K prime, and CK prime is equal to 0 in the first level. So in the first level, I have to write down that for any K, for any K not equal to K prime, I H d over dt c K prime is equal to, so if it is K prime, it is K prime here, it is equal to B K prime K and is it clear where I got this equation? Once again, I used the fact that I'm calculating this coefficient perturbatively. In zero order perturbation, all coefficients K prime not equal to K are equal to 0. The only coefficient K equal to K prime is equal to 1. Therefore, in order to find the first correction, iterative correction, I have to put here 1 times delta K double prime K. Therefore, the sum over K double prime will contain only one term, where K double prime is equal to K, and therefore I have V K prime K here. And on the left-hand side, I have a time derivative. So this is how this equation is obtained, and let me write it down here. Namely, let me write down the solution of this equation, namely C K prime as a function of t is equal to minus I over h bar, integral from minus infinity to t, v K prime K t prime d t prime. Okay, so now I will plug in the form of interaction, use the fact that the interaction is separated on its Fourier component and calculate response on this Fourier component, and then using this formula I calculated density, and multiplying it by charge of electrons I calculate charge density, and therefore I will be able to express induced in the system charge in terms of total charge and calculate the dielectric constant.
Excuse me. Without adiabatic
No, with the adiabatic approximation. Of course, I have to define what happens with the potential at minus infinity. So that at minus infinity, there was no interaction at all. We come to the point of adiabatic approximation very, very soon. But just for coherence of the course, did you do these things? Did you discuss it
in quantum mechanics?
Yes, but this is repetition of quantum mechanics perturbation theory. But now I'm going to solve many-body problem. You see that I'm not talking about single electron. Of course, they are counted one by one when they are not interacting. Okay, what what I will do now is to plug in this form of external potential, not specifying what V is. It's some function of Q, but since all my integrals affect the time variable only, for the moment I will consider external potential, which is perturbation in this form. Therefore, C k prime t is equal to minus I h bar integral but of course, let me v k prime k is integral to integral dr psi k prime no star v r psi k no r. And as I wrote, psi no k is equal to 1 over square root of volume e to the power I k r minus I epsilon k t. Okay, so I have integral over dr, and I have integral. Let's just calculate this one. So v k prime k is a function of t is equal to integral over dr 1 over volume e to the power minus a k prime r plus I epsilon k prime t. Here I have v e to the power I u r minus I omega t plus v star e to the power minus I u r plus I omega t times exponent I k r minus I epsilon k. So when I take integration over r, 1 over omega, I have first of all v times e to the power I epsilon k prime t minus I omega t, and here I have delta symbol q k prime k plus q. Okay, this comes from the first term plus v star e to the power minus I epsilon kt. I should collect all three terms. I epsilon k prime t plus I omega t minus I epsilon kt. And here the delta function tells me that this is delta k prime k minus q. So this is matrix element, and now I'm about to plug it in in the first line. Namely, C k prime t is equal to. So what remains? Minus 1 over h. Here it's 1 over omega. What remains here? Sorry. Actually, omega should be incorporated here. So 1 over omega integral e to the power I u r dr is equal to delta u 0. So this is the definition. So volume is included, of course, in normalization. So now I'm taking integral where the only time dependence comes from here. The integral of e to the power something can be easily taken, but what I will do, I would like to provide convergence of this integral at t equal to minus infinity. Therefore, I will put, instead of omega plus I delta. So what then happens here is I have omega delta. I have delta t in the exponent, which on the lower limit gives me 0, if t is equal to minus infinity. So calculating this integral, I have v delta k prime k plus q divided by I epsilon k prime minus epsilon k minus omega times the phase I epsilon k prime minus epsilon k minus omega t minus plus v delta v star k prime k minus u, the same epsilon k prime minus epsilon k plus omega e to the power I epsilon k prime minus epsilon k plus omega times t. And there is I can be cancelled, and there is a general sign minus in front of everything. And from now on, let me put h bar equal to 1, because I don't want to bother with the constants in front of the basically what I have to get is h omega here. If I'm counting with energies, so I will count h and h bar there. Therefore, in principle, I have h bar in front of everything. It will be also cancelled here and there, but in order to avoid introducing more notations everywhere, I will just drop h bar from the form. This is how to recover it. Okay. Are you with me? Are you understanding what we are doing? Because we will arrive at the expression which we need very, very soon. So what we got, and let me repeat it, ck prime is equal to minus 1 over epsilon k prime minus epsilon k minus omega v delta k prime k plus q e to the power a epsilon k prime minus epsilon k minus omega t minus 1 over epsilon k prime minus epsilon k plus omega v star delta k prime k minus q e to the power I epsilon k prime minus epsilon k plus omega. I'm just repeating the line. And of course, following our perturbation theory, psi k r t is equal to psi k naught r t plus sum of the k prime c k prime not equal to k psi k prime naught r. When we plug it in here, we see that summation over k prime, due to this delta symbol, is reduced to one term. Namely, I have to put k prime equal to k plus q for first term, and k prime equal to k minus q for the second term. Therefore, I can write it down that this is k0 t minus 1 over epsilon k plus q minus epsilon k minus omega v e to the power I epsilon k plus q minus epsilon k minus omega t minus 1 over epsilon k minus q minus epsilon k plus omega v star e to the power I epsilon k minus q minus epsilon k plus omega. And this is just an exponent which we used. Okay. There should be, let me write it this way. Let me write here the exponent 2 e to the power I k r minus epsilon I epsilon k t minus that. And let me put 1 over square root of volume in front of everything in order to keep correct line. So now, what I have to do, I have to take this function, square it, and substitute it into the density operator. When I will square it, what will I take? I will take only linear in V terms. Namely, I will take this one as modulus square, which gives me 1. Then I will take a product of this to that, product this to that, but will not take a cross product of that sort. Why? Because it contains V squared. And I am in the first order of perturbation theory. I'm only keeping term in V. So if I do it, I can write that psi k r t modulus square is equal to 1. Well, it's equal to 1 over volume. And here it's 1 minus something is still yeah, I have to write here something which is related to it will be plus I k prime is equal to k plus q r in the argument of exponent, and here I have to write I k minus q r because it comes from this. Yeah, and when I will multiply it, namely take modulus square of it, k will be gone because I will multiply this term by complex conjugated, and what remains is q. So I'm writing q the result. It's v e to the power minus I omega t plus I q r divided by epsilon k plus q minus epsilon k minus omega minus v e to the power I q r minus I omega t epsilon k minus q minus epsilon k plus omega plus term minus q omega. So in total, as I said, there will be 5 terms. One is coming from square of this, and then, as I said, I will take only products of this term and that, this term and that, but not the cross term which contains the square. So 1 is a density when the interaction is equal to 0. Therefore, all the rest is related to rho induced. So this is induced charge. Namely, I write that rho induced by interaction as a function of r t is equal to minus v over omega times sum over k sigma. I have n k sigma here 1 over epsilon k plus q minus epsilon k minus omega plus 1 over epsilon k minus q minus epsilon k plus. So here I used this fact of random phase approximation, namely I subtracted induced density which is proportional to the same harmonics which contain my perturbation. So this is what I obtained. So I do see that my induced charge is proportional to perturbation, it's inversely proportional to volume, and it contains these occupation numbers which stand here. If I take replacement, namely if I denote k plus q as uk prime, then I can transfer denominator to the same form as here. It will be epsilon k minus q, k prime minus epsilon k plus omega. Therefore, I continue it here, it's minus v over volume, sum over k sigma, and here I have n k sigma minus n k minus q sigma epsilon k minus q minus epsilon k plus omega. So this is basically Lindbergh function, which we already discussed and which Ganesh